In this video, we're going to be taking a look at a couple of moderately challenging trigonometric limit problems. The first one we're going to be looking at is the limit as x tends to 0 of sine of 5x over 3x. Let me write that a little more clearly here. Sine of 5x over 3x. Okay, and looking at this, you can see this bears some resemblance to this limit here. Limit as x tends to 0 of sine of x over x. It's one of the fundamental limits you should commit to memory, and it's 1. We want to make this look like this, or bear this form. So the sine 5x, we can't do anything to that, but we can turn this 3x into a 5x. So what we do here is to do that, we just multiply the 3x by 5/3, because 5/3 times 3x is 5x. But if we do that to the denominator, remember, in order for these two expressions to be equivalent, we can only multiply them by 1. So in order to multiply by 1, what we multiply the denominator by, we also have to multiply the numerator by. So here, I'm going to rewrite this limit. And this 5/3 times 3x, I'm just going to go ahead and write it as 5x. So 5/3 times sine of 5x over 5x. That's the limit as x tends to 0. I'm just going to write the 5/3 out front. Sine of 5x over 5x. But remember, the limit of a constant times a function is the constant times the limit of that function. So this is 5/3 times the limit as x tends to 0 of sine of 5x over 5x. So the limit as x tends to 0 of sine of 5x over 5x is 1, because 5x is just another. Well, we can, to make this a little bit clearer, what we can say is at this point, let's let 5x, let u equal 5x. Okay, so the original limit we had was the limit as x tends to 0 of sine of 5x over 3x. And all the work we've done got this to this form, 5/3 times the limit as x tends to 0 of sine of 5x over 5x. But now we let u equal 5x. So this 5/3 times the limit as x tends to 0 becomes the limit as x is 1/5 u. So the limit as 1/5 u tends to 0. Sine of 5x becomes sine of u. 5x is u. So we have 5/3 times the limit as 1/5 u tends to 0 of sine of u over u. But what's the limit as 1/5 u tends to 0? We know that the limit as x tends to 0 of sine of x over x is 1, but if we have the limit of 1/5 x or 1/5 u tending to 0 of sine of u over u, what would that be? Well, you know, as 1/5 of something goes to 0, then 5 times that something is also going to go to 0. And the best way to show that is u is equal to 5 times 1/5 u, right? So if we plotted on the x-axis, if we plotted 1/5 u, okay, 1/5 u, and on the y-axis we plotted u, we would get a line with a slope of 5. Because for every 1 unit, 1/5 u, we're going to be going up 5 units u. If 1/5 u is on the x-axis, for every 1 unit on the x-axis, we're going to be going up 5 units on the y-axis if u is on the y-axis. But the point is, the closer and closer 1/5 u gets to 0, u is also going to get close to 0, only 5 times as fast. So we know that the limit as 1/5 u tends to 0 of sine u over u, that's the same as, well, we have 5/3 out front here, as the limit as u goes to 0 of sine u over u. Okay, I'm just going to scratch over this here for a minute. So you can see that this is of the form limit as x tends to 0 of sine x over x. Only instead of x we have u. So this is 5/3 times 1. This limit is 1. So 5/3 times 1 is 5/3, and that's the limit here. And I guess I glossed over this, but if you were to just look at the terms here as they are, if you were to just look at this expression as it is, you'll see as x tends to 0, sine of 5x tends to 0, like this. Approaches 0, 0 when x goes to 0. But 3x also approaches 0 when x goes to 0. So here you'd have an indeterminate form. So you'd have the form 0 over 0, which is an indeterminate form. And in previous videos I've done several examples involving indeterminate forms. This is another one. Whenever we do any fancy algebra, U substitution, anything like that, it's because we have to skirt around this independent form or indeterminate form to find a limit. So we're going to work another problem here. And this one's going to be the limit as x tends to 0 of cosine of 2x minus 1 divided by cosine of x minus 1. Or sorry, this is going to be limit as x tends to 0 of cosine of 2x minus 1 divided by cosine of x minus 1. So you look as x goes to 0, cosine of 2x goes to cosine of 0, which is 1. 1 minus 1 is 0. The denominator, cosine of x, as x goes to 0, cosine of x goes to cosine of 0, which is 1. minus 1. You have another 0 over 0 indeterminate form. This means we have to do some algebra to get around it. So here we have this cosine of 2x. Hopefully you remember your double angle trig identities. If not, I'll write the cosine of 2x. There's 3 ways of representing it. First is cosine squared x minus sine squared x. Now, if you make the substitution, if you also remember that sine squared x plus cosine squared x equals 1. So for cosine squared x, you can substitute 1 minus sine squared x. And that's because if you subtract sine squared x from both sides of this equation, you get cosine squared x equals 1 minus sine squared x. So cosine of 2x, so for cosine squared x, if you substitute 1 minus sine squared x, you'll get 1 minus sine squared x minus another sine squared x. So that's 1 minus 2 sine squared x. But alternatively, what if for cosine of x, or for sine squared x, you could substitute 1 minus cosine squared x? And the reason for that is, from this expression here, this sine squared x plus cosine squared x equals 1. Let's say you were to subtract cosine squared x from both sides. You subtract it from this side, you're left with sine squared x. You subtract it from this side, you get 1 minus cosine squared x. So here you get cosine squared x minus 1 minus cosine squared x. So cosine squared x minus, and instead of sine squared x, we write 1 minus cosine squared x. And all this is in parentheses because the 1 minus cosine squared x takes the place of sine squared x. So this minus sign is going to have to be distributed across these parentheses here. So cosine squared x minus negative cosine squared x is 2 cosine squared x, and then minus 1. So the 3 forms you'll see that are cosine squared x minus sine squared x, this form, 1 minus 2 sine squared x, and 2 cosine squared x minus 1. But which form do we use here? So let me rewrite this limit here. The limit as x tends to 0 of cosine of 2x minus 1 divided by cosine of x minus 1. Well, we ultimately we're looking in a lot of, as in the case of a lot of these 0 over 0 indeterminate forms, we're looking to cancel either the numerator, something either in the numerator or denominator. If you see this 2 cosine squared x minus 1 minus 1, you'll see that it gives you a 2 cosine squared x minus 1 in this expression for cosine of 2x. You'll have 2 cosine squared x minus 1 minus another one, which is 2 cosine squared x minus 2. You can factor out the 2, you'll have a cosine squared x minus 1, and you'll see that that's of the form a squared minus b squared, and one of its factors will be cosine of x minus 1. that will not be the case. So I'll go ahead and work it, and then we'll try the others, and I'll show you why those wouldn't be a good idea to substitute here. So 2 cosine squared x minus 1 divided by, this is the limit as x tends to 0 of all this stuff, cosine x minus 1. This is 2 cosine squared x minus 2, still limit as x tends to 0, over cosine x minus 1. You can factor out the 2 here. So 2 times cosine squared x minus 1 divided by cosine x minus 1. And all of that, we can, here we have a constant 2 times this cosine squared x minus 1 over cosine x minus 1. And the limit of a constant times a function is the same thing as a constant times the limit of that function. So that's the same thing as 2 times the limit as x tends to 0 of cosine squared x minus 1 over cosine of x minus 1. And you can see that, hopefully you can see that this numerator is factorable. And one of the factors is going to cancel with the denominator. Cosine of x minus 1 times cosine of x plus 1 divided by cosine of x minus 1. So these cancel here, and we don't have to be concerned with division by 0 because we're concerned with what happens as x gets really close to 0 but not at 0 itself. When x is 0, cosine of 0 is 1. 1 minus 1 would be 0, but we're not looking right at cosine. We're not looking right at x equals 0. So this is 2 times the limit as x tends to 0 cosine of x plus 1. This limit is just 2 times, or it's 2 times this limit. Cosine, as x gets close to 0, cosine of x gets close to 1. So 2 times 1 plus 1 is 2 times 2, which is 4. Now, suppose instead of this 2 cosine squared x minus 1, let's say at this point we had used, so this is the final answer, this is all the work leading up to it, right? And so I'm just gonna delete some of this stuff below so I can show you here. Let's say when we were at the limit as x tends to 0 of cosine of 2x minus 1 over cosine of x minus 1, I guess that's how it was originally written. And for this cosine of 2x, instead of plugging in 2 cosine squared x minus 1, we had plugged in this form here, 1 minus 2 sine squared x. So this will be the limit as x tends to 0 of 1 minus 2 sine squared x minus 1 divided by cosine of x minus 1. We have a plus 1 and a minus 1. They drop out. So these cancel. We have the limit as x tends to 0 of negative 2 sine squared x over cosine of x minus 1. Now the problem here is that this doesn't generate a factor that cancels out with cosine of x minus 1. However, when we made the substitution 2 cosine squared x minus 1 for cosine of 2x, we were able to rewrite this as 2 cosine squared x minus 2, factor out the 2, and what we're left with here, cosine squared x minus 1 has a factor that's equivalent to cosine of x minus 1. One of its factors is cosine of x minus 1 and the other is cosine of x plus 1. So that enabled us to cancel here and get around this problematic cosine of x minus 1 that was causing a division by 0 and leading to that indeterminate form. Here, as x gets close to 0, sine of x gets close to 0, so sine squared x also gets close to 0, as does negative 2 sine squared x, because negative 2 times 0 is 0. And this denominator still gets close to 0. Cosine of 0 is 1. 1 minus 1 is 0. So we still remain with that 0 over 0 indeterminate form, and we really haven't gotten anywhere. If we made the substitution for cosine of 2x, cosine squared x minus sine squared x, we'll see what happens. So this limit, this original limit here, is equivalent to limit as x tends to 0 of cosine squared x minus sine squared x, and minus 1 divided by cosine of x minus 1. Now, of course, this doesn't at all cancel with, this doesn't really generate any factors, perhaps we could write this here as cosine squared x minus sine squared x plus 1, but this here isn't even the difference of perfect squares, because sine squared x plus 1 is not a perfect square. So this form doesn't really get us anywhere, and this is the limit as x tends to 0 of this stuff. As x goes to 0, this term here goes to 1. This sine squared of x goes to 0, and this, we add 1 to it, it goes to 1. So we have 1 minus 1 in the numerator. And we still have this cosine of x minus 1, which goes to 0 in the denominator, 0 over 0 indeterminate form. And we really haven't gotten anywhere. So this 2 cosine squared x minus 1, this particular form of cosine of 2x, this particular double angle formula for cosine, is what turns out to be advantageous here. And you can kind of see that because when you plug this in here, 2 cosine squared x minus 1, you subtract another 1, you get 2 cosine squared x minus 2, and hopefully you'll see that the 2 can factor out, and that cosine squared x minus 1 contains the denominator as a factor. So we have a useful cancellation that helps us get around the indeterminate form here. And hopefully that made that extremely clear for you.